Okay. Yeah. Hello. Hinde. Obrigado. Thank you, Clarice. So, welcome. Thanks for coming. I don't know how many seminars I've given here on courses. A few. I don't. Anyway, and I always talk about the same thing, so that's easy. So this is some work with Clarice, who you know, and Wagner from Curitiba. So this is about over and under dispersion, zero inflation, and some models. So a very quick summary. I'm going to, just in case some of you don't know about these things, I'll give a quick introduction. Then I'll talk a little bit about counting, say a little bit more about overdispersion, underdispersion, and zero inflation. Then talk briefly about this class of models and finish with a couple of examples. So there should be something for everybody. So let me just start. Some quick background. So today I'm going to think about count data. And so we talk about count data being, overdispersed if the variance is bigger than the mean. So if we have Poisson count data, the variance and the mean are equal, but if the variance is larger, we talk about overdispersion. Now, and there are lots of causes, lots of possible reasons that this can happen. Extra variability in the experiment that you're in, correlation, the sampling mechanism, aggregating data, failing to record important possible explanatory variables. Almost everything that happens when you have count data gives you overdispersion. Lots of possible reasons. Just a few quick ones, just to set a background. If you think about taking random sums of random variables, like a Poisson sum of random variables, simple probability theory shows you that you can get a variance which is some multiple of the mean. And it depends upon the types of random variables that you're counting, taking the sum of. Very easy to get. One that you've probably all met is that instead of having a Poisson distribution with a fixed mean, you let the mean have some distribution. In particular, a gamma distribution. Then you get a negative binomial distribution, and its variance is not some multiple of mu, it's mu plus mu squared divided by this index parameter. So you can get that just by having a second level of variability. The means vary as well as the counts. Another possibility, sort of similar to the first one, is you can, instead of just having a log linear model, standard log linear model, you'd have log of the mean, the linear predictor, some combination of explanatory variables. You add in a random variable. With any random variable, what you get is approximately you get a quadratic variance function of this form. So it looks a bit like negative binary. I mean, the point is, it's easy to get models where you have this extra variability. It's easy to think about situations that give you more variability. It's easy to think about mechanisms and models. So let's just have a really, just to keep you all on base, here's a really simple example. There are no covariates, simply counts of movements of a baby lamb. Well, it's not born yet, so it's a fetal lamb before it's born in the womb. And they counted how many times it moved in 240 time intervals. And on 182 occasions, it didn't move at all. And then 41 of these occasions, it moved once. And then on one particular occasion, it was going mad, and it moved 7 times. Yeah? So it's some count data. If you calculate the mean, you get 0.36. The variance, 0.66. That variance is bigger than that mean. Overdispersion. But we might also notice that there's an awful lot of zero observation. Yeah? Quite often it didn't move. And if you look at this, we see there's quite a big spike at 0. What happens if you fit a Poisson model? Oh, look, it doesn't fit very well. It underestimates the number of movements at 0, and it overestimates the number of ones. Doesn't work very well. So we might think about either an overdispersed model or a model that picks up, that does something to account for these extra zeros. And there's lots of models. There's mixed Poisson distributions. There's zero modified distributions. There's so on and so on. Let's just look at a couple. Really just like the negative binomial. I'm going to take a Poisson distribution with a mean, and I'm going to put another random variable v in here. And I'm going to give that mean 1, variance alpha. Well, no surprise. The mean of y is mu. And the variance of y turns out to be quadratic. Just like I said it would if we put an extra variance term. And something else happens. The probability that y is equal to 0 under this model is bigger than the probability that y is equal to 0 under a Poisson model. So we have overdispersion, the variance is bigger, and we have zero inflation. Just by putting extra variability in there. Now, an obvious way would, if you go back to the lamb, you might think, oh, well, look, sometimes it's not moving. And maybe that's different from when it might move. So you can think about a standard model, zero-inflated. A zero-inflated model. So it's really a mixture. So we put some probability, extra probability, that we'll get a 0. And then with probability omega, we get just zeros, and 1 minus omega, we get Poisson. 1 minus omega, we get Poisson again. When you work out the mean, it turns out to be 1 minus omega times lambda. When you work out the variance, it takes this form. And what do you see? Well, for omega bigger than 0, that's extra zeros, zero inflation. Oh, this thing will be bigger than 0. So you get over-dispersion. Well, if you think about this, this is just really a special case. This is just a special case of this guy, where V is a mixture of 0 and mu, 0 and lambda. So let's see what happens when we fit these. So I'm fitting these. If I fit the Poisson model, I get a deviance of 348. Now, when I say the number of V parameters here, what I'm thinking about is V. There's that V, that extra variability. How many parameters does it have? Well, if V, so I've got a Poisson distribution, V is just 1, there are no extra parameters. And there's my Poisson distribution. The negative binomial is going to have mean 1 and an extra variance parameter. Oops. Press the right button. And 1 extra parameter. The deviance drops down to 319.7. Huge change for 1 additional parameter. If I do something, instead of taking a gamma distribution, I take a random effect with a normal distribution, I get something very similar to the negative binomial. If I fit the zero-inflated model, I don't do quite as well. Again, 1 extra parameter. And there's a rather strange one here, which I'm not going to spend any time on today, but it's just a little bit lower, but it has more parameters. Let's just see what these mean. So here's our Poisson. When I fit the Poisson, there's no extra variability. There's a single mean, and that's my distribution. So my mixing, I just have a single mean. When I go to the negative binomial, I have an extra gamma. What I get is I get a mean, and the variability of that V turns out to be 0.24. Up here, there's no variability. I'm just in a Poisson. When I do a zero-inflated Poisson, what do I have? I have 58 omega is 0.58. 58% of the time, I just get zeros. The other 0.42, I get Poisson with lambda. Lambda of 0.85. If I combine that, work out the mean of that, I get 0.36. And the variability of that 2-point distribution is 0.17. And this guy that did just a little bit better, that's a bit like this, but it has an extra parameter. It's a more complicated mixture. So there's some zeros, and then there's 2 mass points. This is very small. This is really picking up that very extreme observation. The means are always the same. It's a bit more varied. How well do these do? Well, here we go. Here's lots of fits of different models. There's the original data. Let's just focus on a few of them. Here's the Poisson. It didn't do very well. Here's the negative binomial. It does very well. Here's the zero-inflated Poisson. It does pretty well too. But what do you notice about the zero-inflated Poisson? The fitted value here has to be the same as the observed. Because when there's no explanatory variables, that happens. These are lots of different, more complicated distributions, and you can see they all do pretty much the same. This one doesn't do quite so well. So the message is, over-dispersed data, zero-inflated data, there's lots of models. There's a link between them. It's quite easy to get models to fit quite well, and the take-home message is that I'm willing to bet that most times the negative binomial distribution will do as well as anything. Almost. Okay. So, now, I need to wake you up again. So it's time for you to do some work. You all learnt to count at school. True? And you all work in an agricultural college where people go and collect data, and they quite often count things. So, how easy is counting? Easy? Well, let's see. What do we know about counting? There's some birds. Many years ago, I used to go with a friend, and they used to count birds like this on cliffs. It's very, very hard. They help. They do line up. They sit on ledges so you can count them. But even then, they hide and they move. Quite hard. Sometimes you can get closer, or you have binoculars, or it helps to get a closer look sometimes. I don't think his intentions are good. I don't think he's really just counting, but who knows? So, how easy is it? Your turn. I'm going to show you some data, and you're going to count it. Yeah? Are you ready? How many dots do you see? All right, wait. You don't have to remember yet, because I know, but do try and remember how many you saw, if you were quick enough. But you're going to have another go. Now you're ready. And because good science says you always do things 3 times, here's a third go. So who are the quick counters? Sylvia. On which occasion? Let's see. What about the first time? Who managed to count the first one? Other than Raphael, who knows how many are there. You counted them. There were 10. Second one? There were 13. I didn't say they were the same. And let's see if Silvio's good when we gave him a bit more time. Oh, well done, Silvio. There were 12. Okay. So how many are there? If you look carefully, you'll see there's some similarity between those dots. Now, I thank Raphael for this, because we came across a paper where they were talking about counting animals. And they talked about counting them. And they said this. They said, it can be quite hard. And detections or counts only include the maximum number of individuals observed in a single group on a given day. So that, they recognize they count them, but if they count 13, there must have been 13 there. Otherwise, So one occasion they may only have counted 10, but if they counted 13, there must have been 13 there. So they're going to record the maximum. Since So, when you did it, the maximum count was the second one, which would have been 13. And in fact, if I put all the things together that you saw, there were in fact 14 of them that I showed you. But on any given occasion, the most you saw was 30. Yeah? So this got me thinking, well, hang on. When people give me count data, I assume they've just gone and counted it. But if they haven't, and they've done it, I count it, I'll count again, I'll write down the biggest number. What effect does that have on the distribution of your counts? So, I didn't know. So, I did what everybody should do. I went to a book. And there's one book about discrete data, Johnson, Kemp and Kotz and things. I went there to see what it had to say. And this was all I could find. Essentially, it says that if you had 2 counts and took the maximum of 2 counts, you would get a mean that looks like this and a variance that looks like that. And these things are horrible modified Bessel functions, and it all looks horrible. But I thought, oh, well, I can calculate that. And then I looked at it, and I thought, well, hang on. You know, that's sort of something. And this looks, I looked at it a bit, and this looks bigger than this. And that wasn't quite what I expected. And there's a good reason for that. They got it wrong. That plus should be a minus. But we'll not worry about it. What does this thing look like? So I thought, well, let's calculate it and see. So I thought, right, let's do the easy thing. Suppose I take 2 Poisson counts. So I count once, I count twice, and I take the maximum. That's exactly what that bit of theory talks about. What do I get? Well, these are the values that you get from the correct version of things in the book, and this is what I get if I just simulate this thing lots of times, because I thought, oh, well, that looks pretty good. And this is what happens when the mean is 4. There's the exact mean and variance. What do you notice? Oh, you notice the variance is less than the mean. I thought, brilliant. At last, I have a really simple way of getting under-dispersion. It was very easy to get overdispersion. Everything leads to overdispersion. Getting under-dispersion in a simple way, it's not so simple. But this is a process. And so the under-dispersion you get, if you look at the variance mean ratio, in this case, when mu equals 1, it's 0.67. And when mu equals 4, oh, it's pretty close. That looked interesting. So I thought I should explore this a bit more. So the mean and variance seem to depend upon mu, but maybe the ratio doesn't that much. And if I plot that dispersion, the mean variance ratio, oh, notice it's pretty, as mu gets large, it's remarkably flat, constant. There's a little bit of change here, but really very, very little. It may be that it hardly changes. This is a numerical problem almost. So it seems if I take the maximum of 2 Poissons, I get about a variance that's about 2/3 of the variance of the original. What happens if I take more? Suppose I take n of them. Well, this is what happens. So if I take 1, that's Poisson. So as I vary mu, my variance, my dispersion is 1, variance equal to the mean. This is the case we just looked at with 2. It stays pretty constant. This is all done by simulation. I have no theory, no horrible expressions out here. It was bad enough for 2, let alone more of them. But see what happens? When we get 3, it's smaller. 4, it's smaller, and so on, and so on. So I can get under dispersion. But, in fact, if you look at this, I can only get certain values. I get that value there, this value here, and so on and so on. I don't seem to be getting just any old value. I can't get a value between 1 and 0.67. That's a bit worrying. And I thought, now, when I showed you those points originally, some of them you saw every time. And those are the blue ones. You always saw the blue ones, and on some occasions you saw some of the black ones. So what would be the impact of this? Well, this wouldn't, just think about it. It would say that you're counting things, so every time you count the easy ones and some hard ones. So every count is all the easy things plus some hard ones that vary. When you take the maximum, Well, the maximum of the easy ones is always just the easy ones. And so what you then get is the maximum of the hard ones. And if you allow these to have different means, these are the easy ones to count, these are the hard ones, a little bit of arithmetic says you can get a dispersion that looks like this. It depends upon the ratio of these means, and this is this ratio that depends upon, this is the ratio that depends upon the number of things in the sample. And let's not worry about the arithmetic, but what you can see is what happens is if I take 4 of them, and as I vary this ratio, my dispersion go anywhere from the value that the ratio I get, all the way up to close to 1. So I can get anything in between when I do this game. So once I've thought about that, we have a process that we can get any sort of dispersion. Okay. And what happens if you take over-dispersed count instead of taking Poisson count? Well, you can just get more variability, and you can go between you're having a dispersion that's more than 1 to less than 1 as you vary them. So we actually have a process that can lead to all sorts of values for the under-dispersion. So that's pretty much the first part of the talk, I think. Oh yes, because normally at this point I say over to Clarice for some models, but on this occasion I'm doing it all. So what would be nice, what would be really nice, would be to now have a model that we can put in zero-inflation, over-dispersion, under-dispersion, all of these things in the same sort of frame. Let's just remind ourselves of a few things. If I look at the difference between the variance and the mean, for the Poisson case, this difference is going to be 0. Under-dispersion, less than 0. Over-dispersion, bigger than 0. And we've talked about this index, this dispersion index as well. Could be bigger than 1 or less than 1. Now, let's look at the Poisson model. We know that variance is equal to the mean, and this S is equal to 0. The negative binomial model, what happens? We had a quadratic variance function. So S, the excess variability, is gamma mu squared. And if you did a Poisson log normal to other things, they all have the same sort of variance. There's a funny negative binomial distribution, which has it's a different way of mixing a Poisson and a gamma, and it gives you a variance function of this form, mu plus gamma mu. And so that's just a scaled version. And here S is gamma mu. And it's the same variance function as a quasi-Poisson distribution. The variance is proportional to the mean. And it also turns out to be the same as Neyman-Taibé. If you take a Poisson inverse gamma, so you're mixing, you then get gamma mu cubed. So you can have an Sx, which is mu cubed. When you look at these things, you suddenly realize, well, what have we got? We've got gamma times some power of mu. So wouldn't it be nice if you could have a model where that was the variance function, and you had S of x some gamma times the general power of mu? We thought that a long time ago. And we know that John Nelder also suggested this at one point, but I can't find John's suggestion. And for a long time we've thought about how this might happen. And Bent Jorgensen, who used to visit here, and he sadly died over a year ago, Bent was interested in Tweedy models, and so if you take a Poisson, conditional x given z to be Poisson, and make z a Tweedy distribution, what you get for x is a Poisson-Tweedy distribution. And it has moments. The variance of z is exactly what we want, this beast, and when we put it together, we get exactly the variance function that we want. So that gives us a nice family for doing what we want, overdispersed, underdispersed, and other things. And in the Tweedy family, there's a whole bunch of models with different variances, and I've mentioned these. It's only the Poisson distribution that's discrete, but that's not a big issue. When you put these together, you get a whole bunch of different, you can get all sorts of different distributions, where your S has different forms. So it could be 0, it could just be a constant, it could be constant times mu, different powers of mu. And there's one special case where gamma, where you have a negative, where you generally you get overdispersion. You get zero inflation as well, but you can get zero deflation. Now, so this is where we want to be. We want to have a general model, general regression model, and we want a variance function that looks like this. And that includes all the sorts of things we might like. Well, almost. I'll come back to that in a second. How do you fit these models? Well, it's a bit of a pain, but it's doable. You can use a quasi-likelihood type method for betas, and you can use the Pearson residuals effectively to estimate these variance parameters. And so you can calculate this power parameter in the estimation process and the gamma. And here's the added part. If we allow gamma to be negative, we can get under-dispersion. That'd be brilliant. Here's the bad news. If we do that, there isn't a probability model within the family. So what we're doing is we're simply using this as an estimating method to fit these models. There's no probability distribution. It's like lots of quasi-likelihood models. So once gamma's negative, life is a little trickier, but the family gives us a way of estimating these things. And we have code. Wagner has code to do that. Right? So let me look at a couple of examples. So here's some simple morbidity data. These are counts of respiratory disease in Curitiba. And there's observations over time from January to December over a 11-year period. And you can see, if we look at the counts over time, we've got very strong cyclical pattern. Oh? And that's to do with other things that are measured, rainfall maybe, temperature, and so this is measuring disease by, so as the rainfall goes down, the respiratory disease, as the rainfall goes up, respiratory disease. And when the rainfall goes up, the temperature goes down, so yeah, same thing. So we've got 3 weather covariates, and we've also got this temporal cyclical pattern that we might incorporate as well. And that's what was done in some modeling. Let's just see. So this is an intercept. Here are these two terms here are just sine and cosine terms to bring out this seasonal element. And then there's explicit additional effects of precipitation and temperature. Here's the results from the Poisson-Tweedie. Here's the results from a fitting a Poisson model. What do you notice? Just look at the parameter estimates. What do you notice about the parameter estimates? They are pretty much the same. And just to help you, here's the ratio of the parameter estimates. You can see they're almost all about 1. No surprise. That's what happens with quasi-likelihood. That's effectively what happens. You get the same parameter estimate. what happens to the standard errors? Here's the standard errors from the Poisson model, and here's the standard errors from the Poisson-Tweedie. What do you notice about these? They are much bigger. Oh, and just to help you, they're all about 3.5 times bigger. Why? Well, because the data is more variable than a Poisson distribution. It's over-dispersed. And so these standard errors become bigger, and so once you take account of this, some of these terms no longer look to be significant. Now, let's just see what happens. Here's our gamma parameter, which is positive. So that says we've got extra variability. And P is between 1 and 2. So we're between quasi-Poisson and negative binomial. It's got a large standard error. You get very similar results for almost any value of P between 1 and 2 here. Very similar. But we do get an estimate of it, but you can see it's very imprecise. But all within one framework, we're fitting this model, and we can see P and the overdispersion. Now, here's a second example. This is looking at the production of cotton. So here's cotton plants, and they're looking at the production of these bowls where the cotton is. I've been to Lavras too much coffee there. And what they're looking at is what's the effect of defoliating the plant? Well, does that help production of cotton? And so it was a completely randomized design. There were 5 replicates, and they had vases with 2 plants, and they applied different levels of defoliation. They took off none of the leaves, 25% of the leaves, right up to taking all the leaves off. Yeah? And they did this at various cycles in the growth. And then they counted the output. The response was the number of these things, cotton bolls, at each culture cycle as the plant progressed from vegetative, flower, blossom, fig, which is the fruit, and then finally the appearance of the cotton. And so they looked at what's the effect. And this is the sort of thing that you see. That this is the number produced, and this is the defoliation level. And so if you don't do any, you get that number. This is in vegetative phase, and as you take off more and more, production seems to go down. But it varies. It's different in the different stages. Blossom, do it in the blossom stage, you get a big drop, and then it doesn't really change much. The fig stage, it's not initially affected, but when you take off lots of leaves, then production drops. So there's clearly a relationship between defoliation, the sort, and the season that we're looking at. Now, when you calculate within each of these, for the replicates, when you calculate the sample mean and variance and plot them, that's what you get. Here's the line of equality. That's where the variances and means would be for a Poisson distribution. They're all down here. Much less variable than a Poisson distribution. Okay? So, what's going to happen? Well, here we go. Maybe. So to try and pick up these trends, we're simply going to fit a quadratic. There's not lots of time points, so let's just use a quadratic. Quadratic over these levels. Second order. You could fit millions of different models to this. You can fit them all. You can fit most of these in package MCGLM. There's lots of other packages that you can fit them in as well, like Gamels or something like that. What do we get when we use Poisson-Tweedie? So here we go. What we've got is an intercept, and we've parameterized it so we've got the linear and quadratic effects in each of the different stages: vegetative, flower, blossom, fig, and bulb. Poisson-Tweedie estimates, Poisson estimates, and just to help you again, the ratio of the estimates and standard error. Well, it's obvious, isn't it? Again, the estimates really do not change. That's quasi-likelihood. Poisson estimates don't change. It's pretty much the same, ratio of 1. What happens to the standard errors? Here's the Poisson standard errors. Here's the Poisson-Tweedie one. And when you look at these, they're considerably smaller. Because the Poisson distribution assumes the variance is equal to the mean. And the variance is, we saw, is smaller than the mean. So these are too big, these are smaller. And in fact, the ratio of these is pretty much about a half. These are about half the size. So what happens is that some of these things, which are not significant here, would be significant. What do we see about our model? Well, look, gamma is estimated as negative. That tells us we have under-dispersion, a negative additional term, a negative S term of under-dispersion. And our P pretty much estimated at 1. So it's very much as though we had a variance function, you know. What would it be? It would just be mu plus, gamma mu. Only gamma's negative, so in this case it's mu minus 0.810 mu, which of course is, what is it, 0.19 mu. So that's like a scale parameter that is less than 1. So it's very like a quasi-Poisson model. And you get very similar estimates if you did a quasi-Poisson model. But the point is, we only have to fit one model, and it estimates these things, and we can see what might be a sensible model. It's possible to get a profile likelihood for P, and here we can see that you really need to be quite close to P equals 1. It's quite precisely estimated. You don't want to move too far away from that, otherwise profile likelihood drops off. So, to summarize, well, okay, so you can then fit the models, and you get the fitted model, and you can put on the right sort of curves using the correct variability, which of course is much less than you would have from a Poisson distribution. So it says, it thinks you have more significant results by taking account of the fact that there is less than Poisson variability. So, let me summarize. Under-dispersion is less common than over-dispersion, and it's quite hard to think how it happens, but I hope that now you can see there is a simple way in which you can get it. Actually, explicitly modeling that maximum things hasn't been done. Maybe something that people could think about taking up. A general family of models, though, are the Poisson-Tweedie, and they can handle, in a quasi-likelihood framework, overdispersion, underdispersion, and zero-inflation. So they give us a broad family of models. But it's all within a quasi-likelihood framework. And implicitly, because we get this estimate of P, in essence, this framework picks for us likely probability. So it says, well, we could fit a Neyman type A model or something, and we get so because we estimate the power parameter, we get some indication of what other models might be appropriate. Well, there's some few references, mainly to the work of Wagner, who wrote the code, and there's an R package to do this. There's a paper summarizing all of what I talked about, not all of what I talked about, some of what I talked about in statistical modeling, which will be out very, very soon, because we've just seen proofs. And thank you very much. Perguntas a Clarice. No question?